doing fine. Significant figures. So all measurements have uncertainty, and the way we keep track of that uncertainty when we do calculations is something called significant figures. Learning about significant figures is a little bit like learning to play a complicated board game. And I can read you the rules, and then you start playing the game, but it doesn't really make sense until you've made some mistakes and the other players correct you and say, no, you can't do that. So bear with me as I give you these rules, and hopefully by the time we get through all the examples, it'll make a little more sense. And I will tell you that I want you to learn about significant figures. Significant figures, though, are not a critical part of Chem 10. Okay, I'm teaching you about them because most of you need to take Chem 3A or Chem 1A, and you will need to understand them in that class. So I'm going to teach you significant figures. There will be some test questions on the first exam. There may be a couple on the final exam, and we will practice using significant figures the whole semester. Okay, so that's the importance of this subject. So with significant figures, when we're looking at a measurement, it includes all of the certain digits and the first uncertain digit. So when we're counting significant figures, when we're identifying which digits are significant, any non-zero digits always count. So this number, 3,456, it has 4 digits in it. 3, 4, 5, and 6. Each of the numbers is called a digit. None of those are zeros. Okay, so if it's not a zero, we count it. So we say 3,456 has 4 significant figures. Significant figures is really long, and so we call them sig figs for short. It's the zeros that get a little confusing. There's 3 different kinds of zeros. Leading zeros are the one that precede all the non-zero digits. So they come at the beginning. We read from left to right, from left to right, and so zeros that come at the beginning of the number are called leading zeros. They are never counted as significant figures. The only reason these zeros here are here is to hold a decimal place. They don't really reflect a measurement, and so leading zeros don't count. 0.048, we would say, has 2 significant figures. And those 2 significant figures are the 4 and the 8. The zeros are not significant. Are they important? Yes, they're important. If we don't write them, the number changes in value. So they are very important, but they're not counted as a significant figure. Then we have captive zeros. Some books call these trapped zeros or interior zeros. These are between non-zero digits. They're sandwiched in. So in this number 16.07, this 0 is stuck between the 6 and the 7. Captive zeros always count. So leading zeros never, captive zeros always. So we would say that this number 16.07 has 4 sig figs. All of the digits are significant. Then there are trailing zeros. These are the ones that are the most confusing because sometimes they are significant and sometimes they are not. These are the zeros that come at the end of the number on the right side. They are significant only if the number has a written decimal point. So this number, 9.300, those are the trailing zeros. There is a decimal point in the number. It doesn't matter if the decimal point is before the trailing zeros or after. If there's a decimal point, the trailing zeros count. So this one, all the digits count, 9, 3, 0, and 0. That has 4 sig figs. The number 150, this is also a trailing zero. There's no decimal point though. We understand where the decimal point would be, but it's not actually showing. If there's no decimal point showing, we're going to say that those are not significant. Really what it is this number is ambiguous. It's not clear if that 0 is significant or not. And so then we're going to assume the worst and say that it's not significant. Oops. 150. Because when we record a measurement, we are implying that the uncertainty lies in the last digit. And so here, this means that we know this, we recorded this measurement, whatever it is, and this is the estimated digit, but we're certain of the hundredths place. The thousandths place is where the uncertainty lies. In the number 150, it's not clear. And so we're going to assume the least amount of precision because that will cause the fewest problems overall. So we're going to say, well, there's no decimal point, so we're going to assume that the uncertainty is in the 5, and that 150 means it was measured between 140 and 160. There was estimation in the tens place. And then there are exact numbers. We don't run into these a lot, but we do a little bit, and so we need to understand what they are. We could say that exact numbers have an infinite number of significant figures. You may say, but you said all measurements have uncertainty. I did. Exact numbers don't involve a measurement. They often involve counting. If I count my children, 1, 2, 3, 4, 5, 6, is there any uncertainty in that? No, there's exactly 6 of them. If I count the students in the room, is there any uncertainty in that? No. Counting is exact. It's a particular number of objects. Other examples are things that are defined or numbers in equations. So 1 inch equals 2.54 centimeters. That is an exact conversion factor because of how the inch was defined. The inch was defined relative to the centimeter. They did that, I don't know exactly when they did that. The inch precedes the centimeter, but they kind of redefined the definition of the inch so that it would be exact with the centimeter. Other examples would be 1 foot equals 12 inches. That's how those units are defined. A foot is exactly 12 inches. There's no measurement in that. We take a foot and we divide it into 12, and each of those is an inch. I think there's a slide missing. So we'll make something up. We need to practice these. So let's practice our significant figure counting. 2.7503. How many significant figures? 5. All the non-zero digits are significant. The 0 is a captive 0. How about 0.0003? Only 1. Leading zeros never count. How about 17? 2. Now, if that was, let's see, that's 17 meters. What if I said 17 eggs? That's an exact number, right? Because that was a counting number, so we'd say that it has an infinite number of significant figures. But with this one, just because it happens to be a whole number does not mean it's exact. Okay? You have to look at the unit and see, well, was that counting or was that measured? 17 meters, I took a meter stick or something and I measured, and it was kind of a rough measurement, and it's just to the nearest meter. It doesn't mean it's an exact number. Let's see. $5,750 miles. 3. Because this 0, trailing 0, there's no decimal point in the number. How about that one? That one also has 3. Okay, in this one, I wrote a decimal point there. Did I have to write that? No. I wrote the decimal point there, and because there's a decimal point, the trailing zeros are significant. Any questions? So we have learned about exponential notation or scientific notation. And one of the great things about scientific notation is that we don't have to worry about those trailing zeros. So an advantage of scientific notation is that the number of significant figures can be very easily indicated, and we're going to need fewer zeros to write very large or very small numbers. So this number 300 with a decimal point, so the decimal point tells us those trailing zeros are significant, but this is still a little bit awkward. When we put this into scientific notation, it becomes 3.00 times 10 to the 2. And now in scientific notation, all of the digits in this decimal portion are going to be significant. There's never going to be a leading zero, and there will never be a trailing zero without a decimal point. So when it's in scientific notation, it's much easier to identify the number of significant figures. So here's the example page that I was looking for. So we got extras. How many sig figs in each of the following measurements? How about that first one? 4. No zeros, that's easy. 0.053. 2. Leading zeros don't count. 35,000 miles. 2. Officially, we'd say that's ambiguous. Okay? What happens, though, is we don't want to take a number like 35,000 that was most likely just a real broad estimate. You know, they're saying it's about 35,000 miles. You got a question? Okay. About 35,000 miles, and then use that in a calculation and end up with some very, very specific number when that number is not that specific because one of the numbers used to calculate it was just a big guess. 402.5 kilograms. How many sig figs? 4. The zero is trapped. The zeros are the ones you have to worry about. 3.500 times 10 to the 4th miles. 5. No? 4. I'm going to write 5. Okay, so I love hearing your answers because even incorrect answers can really help us because that helps me to know what is not quite being understood and maybe where your mind is going. So 3.500. So then there's these digits over here, and the person who said 5 was probably thinking of, maybe this 4 is significant also, and that's a reasonable thing to consider.
So wouldn't it go one decimal place farther than the 2 zeros are now?
Well, when we write this number out, see, that's a very good question. When we write this in decimal form, it's going to look like 35000, right? Okay, 35,000. Just like the one above that had 2 significant figures. But writing it this way, what we're saying is that the uncertain digit is in the tens place. It was measured to the nearest 10 miles. Without using scientific notation, it's difficult to indicate that to the reader, that I measured this to the nearest 10 miles. Because if I take this number and I put a decimal point here, then I'm suggesting that the uncertainty is over here.
So you wouldn't carry that decimal point that's already there?
Not for considering significant figures. Okay, very good questions you're asking. So when you take that, if you take that number and put it into decimal notation, you would write 35,000. Okay, the thing is that in terms of significant figures and where the uncertainty lies, it's difficult to indicate that the uncertainty is in one of those middle zeros. Because if we don't write a decimal point, then it's ambiguous, and we're going to assume that the uncertainty is way over here. So one way you can get around that, just kind of as notes to yourself, because not everybody reading it's going to understand, is to write it like I did here, where we underline the uncertain digit. So that's one method of indicating for those ambiguous zeros, but that's not a universal thing. So when we want to be clear about sig figs with those trailing zeros, scientific notation is the best way to go. So scientific notation has two big advantages, well actually three. Some numbers are too large or too small to fit into your calculator, and you have to use scientific notation. Scientific notation also avoids miscounting the number of zeros on either side. And it allows us to very, very easily indicate where the uncertainty is in a number. So when we're looking at a number in scientific notation, this is the decimal part. All the digits in front of that time sign are significant. These are trailing zeros, right? But there's a decimal point. There has to be a decimal point if there's trailing zeros, because the first digit can't be 0. So there's never trailing zeros without a decimal point. Those would be insignificant. There's never leading zeros because the first digit has to be a non-zero digit. So scientific notation, you just count all of them. Any questions? Yes?
So if they would have put one more zero, then would have the uncertainty have been 5? Because if they would have put 3.5000,
Mm-hmm.
because of the numbers by on the last one.
That's a decimal point, by the way. So now there is 1, 2, 3, 4, 5. This is 5 significant figures, and that would be equal to 35,000 still. That was a comma, with a decimal point, and the uncertainty being over here. Yeah, and you could have even more zeros. You could have 33.500000. You could. Be unusual, but you could. So that's still going to be 35,000 point. So 1, 2, 3. Then we'd have 2 zeros after the decimal point. Okay? Good questions. Anybody else have questions?
So how many significant figures are there in those numbers?
Okay, so in this guy, we're going to count all of these. So the 3 and the 5, and then there's 5 zeros. So that would be 7 sig figs. And also in that one. And this guy over here, because there's a decimal point, that would be 5, just like this one. It's when that uncertain digit is greater than the ones place that things get tricky in decimal notation. If the uncertain digit is in the ones place or in the tenths or hundredths or thousandths, we can write it in decimal notation and see the uncertainty very well. But with large numbers, it doesn't work very well. And so scientific notation is awesome. So it's good to understand sig figs for this class. I want you to give it your best shot and at least become somewhat familiar with it. So in your next chemistry class, they'll teach it to you again. And that time, it'll probably make a lot more sense. So try this. Scientific notation, you have to get, okay? You're going to have a hard time passing the class if you don't get scientific notation. So throughout the class, I'm going to tell you some things. It's like this one, yeah, it'd be good to know, but you could blow this one off and be okay. And then, but this one, no, you have to get it, okay? And life is that way too sometimes, right? Because you can't always do everything. You want to, but you just can't. You know, your calendar gets too full and you've got all these things you're supposed to go to, but you can't be in 2 places at one time. So you have to pick what's more important, okay? So I'm going to try to help you identify that throughout the class. Sometimes we have to round numbers, and so we're going to review the rules for rounding off. So if we're going to round off a number, we look at the first digit that's going to be removed. and we ask ourselves, is it less than 5 or is it 5 or greater? If it's less than 5, we round down, meaning the preceding digit stays the same. So if we have 5.64 and we're going to round to the 10th place, we're going to look at the 4 that we're getting rid of. We say, okay, well that's less than 5, and so we'll round to 5.6. So why might you have to do this? Well, you could be given a problem that says, okay, here's 5.64, round that to 2 significant figures. So the 5 and the 6, the 5 and the 6, those are the digits you want to keep, and then you look at the first one you're getting rid of. If there's ones after that, completely ignore them. They don't matter at all. It's just the first one you're getting rid of. So this one is going to round down because 5.64 is closer to 5.6 than to 5.7. That's the big idea behind rounding. If the digit to be removed is equal to or greater than 5, we'll round up. We'll increase the preceding digit by 1. So if it was 5.68 that we were rounding to 2 significant figures, it would round up. Because we're getting rid of the 8. 8 is 5 or greater, we round up. 5.68 is closer to 5.7. 3.861, if we're going to round that to 2 significant figures, we're keeping the ones place and the tenths, and we're going to get rid of the 6. That would also round up. This 1, he doesn't matter at all. Sometimes we have a series of calculations. There might be multiple steps, and you do this part, and then you do this, and then you do this, and you end up with a final answer. We shouldn't round the individual results, because that can introduce error. We should round the final answer. But you have to look at your individual results and identify how many significant figures they each have so that you can decide how many significant figures to use in your final answer. And that's what we're going to talk about next, is how do we deal with sig figs in calculations. So there are 2 classes of mathematical operations that we're going to talk about. Multiplication and division are related to each other. They are opposites. And so they have one rule for dealing with sig figs. And then adding and subtracting are a different animal, and those have a separate rule. We'll talk about multiplication and division first because it tends to be the easier. So in words, for multiplication or division, the number of sig figs in the answer is the same as the measurement with the smallest number of significant figures. So what does that mean? That means that we're going to look at the numbers that we are multiplying or dividing. First, you just do the multiplication and write down whatever your calculator shows you. Your calculator doesn't understand significant figures. And then to find out how many of those you should keep, you're going to come back and look at the numbers that you started with and identify how many sig figs are in each of those. So 1.342 has how many sig figs? 4. And 5.5 has how many? Now this is the tricky part. Which number is smaller, 4 or 2? 2. That's not tricky at all. This is the smallest number. That's all we're doing. We're taking the smaller number of sig figs, and that means we're going to round this answer to 2 significant figures. So we're going to keep this ones place and the tenths place. We're looking at the next place. That's the 8 is the first one we're chopping off. And then we apply our rules for rounding. So that's going to round up, and our answer is 7.4. Any questions? We'll do more examples. Adding and subtracting. This is a little different. Here we're looking at the number of decimal places, not the number of significant figures. And I'll show you why that is. So let's say we were adding these two numbers, 7.83 and 23.445. So 23.445, which digit is uncertain? The 5. It's always the last digit. In 7.83, which one's uncertain? The 3. Okay, so we add this on our calculator, we get 31.275. We write that down. But then let's look at this. Where did this 5 come from? It came from adding this 5 to nothing. Was there uncertainty in that 5? Yeah, that was an estimate. Do we know anything about the thousandths place in the other number? No clue. We're going to assume it's 0, but we have no clue what it is. So this 5 that we get in our answer, is there uncertainty in that? Are we sure it's a 5? What if this wasn't really a 5? Then this wouldn't be a 5. There's uncertainty in this. Do you see that? If we take a 5 that we just guessed at it, and we add something else to it, we can't be certain of the result. There's uncertainty in this digit. How about this 4? Is there any uncertainty in that 4? No. Is there uncertainty in the 3? Yes. So when we add the 4 and the 3 together, we get 7, but are we certain? No. So that digit has uncertainty. How about this 4? Any uncertainty? Nope. How about the 8? Any uncertainty? Nope. So when we add the 4 and the 8 and get 12, is there any uncertainty in the 2? No, there isn't. And the rest of these digits, there's no uncertainty, and so when we add them together, there's no uncertainty in the result. But our numbers, when we write them, we keep all the certain digits and only one uncertain digit. Because if there's uncertainty in the hundredths place, do we really know anything about what's in the thousandths place? No. So we're not going to write that down. So we're going to round this to 2 decimal places. We're dropping the 5. 5 or greater rounds up. And so we're going to record this as 31.28. Because now, when we give this result to someone, they would say, oh, there's uncertainty in the hundredths place. And that reflects where that result came from. Because sometimes you'll have one result that's very precise and another one that's kind of an estimate. And we want our total to reflect how well we actually know that number. Let's see if I can come up with an example. I gave one yesterday in Tulare, and it didn't really make that much sense, so let's do a different one. So let's say you're measuring the wall of a building or something, and it was 120 feet. And this was a very rough measurement, because maybe you pasted off or something. You didn't even have a tape measure that long. So you figured out how long your steps were and you pasted off. And so it's really a kind of a guess of a number, 120 feet. So it's that distance, the length of the wall of this building, and then it's a little bit more. Maybe it is, you measure the little bit extra, and you've got a ruler that works for that, and so you can see that it is 3.75 feet beyond that. And then we add these together, and your calculator would give you 123.75 feet. So if you were measuring this and it was 3.75 feet past the end of this long building, can you really say that the distance is 123.75 feet? No, because the distance of the building, the length of the building, was estimated. You're guessing within 10 feet. So we don't want to report this and mislead people into thinking we know that distance more accurately than we do. So what would significant figures tell us to do? Well, let's look at the uncertainty here. 120 feet. As it's written there, we're going to have to assume that the uncertainty is in the tens place. 3.75, the uncertainty would be over here. So then which of these digits in the answer have uncertainty? Does this 5? Yeah, that's uncertain. How about the 7? What did the 7 get added to? Well, we had to assume 0, but we know nothing about the decimal places of that first number. So this one's uncertain. How about the 3? 3 was added to this 0, but that 0 is uncertain. This is uncertain. And the 2 is uncertain. So how should we round that number? To 2 decimal places. Should we round it to 12 feet? Wait a minute. How can we round 123 and get 12? So I have some yard work I need done. And I'll pay you $123.75 to come and clear out the garden. All the weeds are still. But we'll just round it off so that we don't have to deal with the cents, and I'll round it off to $12. You like that? Is that good? No, that's not good. I'm cheating you out of over $100. When we round a number, we can't change the value of it. And when we round numbers and we're dropping digits to the left of the decimal place, in the ones, the tens, the hundreds, the thousands place, we can get into trouble. And this is a very common mistake that students make. This needs to be rounded to 120 feet. And you may say, well, how can you add something to 120 feet and have the answer still be 120 feet? Because the 120 feet was a very rough number. Adding a little bit more on top of it really doesn't matter. Think of a big semi-truck. It's got mass, right? Does its mass change really that much if you throw a ping pong ball on it? No. It's this little tiny bit. So what's the mass of the truck? Well, you put it on the truck scale over on Danube Avenue. You put it on the truck scale, and it's not going to give you a mass to the nearest ounce or half of an ounce or anything. You know, it's probably, I don't know, 100 pounds, 1,000 pounds maybe. Maybe 100 pounds would be my guess. Well, the ping pong ball weighs less than the uncertainty of the measurement of the truck, so adding it on really just doesn't matter at all. So how do we deal with a number like this that we have to round? The best thing to do is to put it into scientific notation, because you never run into this problem of rounding off a number and changing its value. 123.75 in scientific notation, we'd move that decimal point after the 1. 12375 times 10. And then we're going to count how many places did we move the decimal point. We moved it 1, 2. So the exponent is 2. 123 is bigger than 1. So the exponent is positive. So here's our result in scientific notation. And then we look at this and we see, oh, we need to round this to we need to keep the 2 and drop everything else. Now we can cut those off without changing the value of the number. So we would round to 1.2 times 10 squared feet, and we don't run the risk of going to 12. Any questions? Yes?
Why don't you just do 124?
Why not call it 124?
You said that rounding off to the upper one if it's more than 5.
Okay, that's a good question. If we were rounding to the nearest foot, we would call it 124. The problem is that there's uncertainty in the tens place. And so when we write the measurement, we want to include the certain digits and only the first uncertain. So we can't really put in the ones place because we're uncertain about the tens. So we really can't say anything about the ones, even though we added a number to it that was much more precise.
So you can just disregard the 3.75 in the first place.
Yes, yes, actually. So sometimes, not a lot, but every once in a while, you add some numbers together and it's like, wow, I didn't even need to bother to do that. Because these numbers are so small compared to the uncertainty in one of the big numbers that they really don't matter. Just like throwing a ping pong ball on a semi-truck. Okay? Any other questions? This is the make up the examples page. Oh gosh, we are out of time. We'll have to finish this later.